good. Yeah. Okay. I think we're well set, right?
Yep.
All right. Okay. Sorry for a little delay. And thanks for coming despite all this miserable snow that goes on and on and on and never ends. I'm very happy today to introduce Nolan Koblischke from the University of Toronto. Nolan is a grad student there in the team of Joe Bobby, but he's been also collaborating with a bunch of folks at Polymathic on a number of things. But today Nolan's gonna be telling us about AION-Search, and he is going to try to answer the questions: can vision language models spot anomalous galaxy images, without further training? And I think that's a very interesting question, very related to some of the stuff we've been doing here at AstroAI. So without further introduction, Nolan, thank you so much for visiting. Sorry for all the delays.
Oh yeah, all good.
Thank you.
Thanks. Okay, yeah. Thanks so much, Raphael. So I'm going to be talking about how we built a search engine for galaxy images that allows you to search for images using text, which is a brand new capability that you haven't before been able to type in merging galaxies of tidal tails, and out of 20 million images get the images that match your text query. And the nice part about this is that it works for anything that you could describe in text, or it should work. You can at least try it. So you can search for like edge-on galaxies with dust lanes, a face-on spiral with a ring-like structure and a core, a single red galaxy, star-forming galaxy. And these are real results out of 20 million images, that it can return the ones that match what you're looking for. And so this is like very different than how you would go about finding these objects before, where if you're very interested in edge-on galaxies of dust lanes, you would get experts to look over 10,000 examples and then have them label whether they are or they aren't. And then you would train a classifier to then run that over 20 million images, and then you would look at the results from that. But now you can at least try to type it into our search engine, and hopefully it'll bring up the matching galaxies. And so you're probably wondering, how we made this, which I'm going to go into. And also I'm going to go into like stress testing it and investigating where it fails. And I'll go into how we're actually using it to build a catalog of objects that we're interested in our group in Toronto, and a little bit of future outlook as well. So in order to build a search engine that works with text, you need a data set of images and the descriptions for those images. And what was surprising to us is that ChatGPT can write galaxy descriptions that are, decently accurate. And you can read some descriptions here, like this one says, a peculiar irregular emerging galaxy system with a dual luminous nuclei and tidal features, which is, pretty well matching with the image that it's describing. And so this was, a big surprise that ChatGPT was probably trained on stuff like galaxy zoo forms and, figures from papers. And so it was able to, and also like, even training data beyond that about knowing what an arc looks like and knowing what, different colors meant. And so it was able to develop this ability to, without any further training, write these descriptions.
So sorry for interrupting. Is ChatGPT 4.1 what you're finally using for this system? Descriptions generated with that model, or?
Yeah, I'm going to talk about exactly how we picked that one. It was a mix of performance and cost. Yeah. Good question, and I'm happy to take questions. So the general idea is that if you then have a data set of descriptions of galaxies, then you can make a search engine. At the very least, you could have descriptions for like 1 million galaxies, and you could control F, edge on, etc. Or if you want to be a bit more, complex, but more flexible, you could turn these descriptions into embeddings. So these are just, vectors that describe the text, and you could search through, and try and find the closest vector embedding of the text that matches your query. And so, I'm going to show you that we would like to do this. We would like to generate descriptions for a huge amount of galaxies, but this is actually going to be costly. So we found a low-cost solution. But before we get there, I made a big claim. I made the claim that these descriptions, describe what's in the image, which is something that is not obvious. And so we had to figure out how to evaluate the actual quality of these captions. And, so we made a benchmark, but one of the constraints is that we wanted the actual description generation process to be very general. So we couldn't, explicitly ask GPT, how many spiral arms are in this image, because that's not what we want to evaluate. We want to evaluate the quality of the general descriptions so that, like, if there's a lens in the image, like a gravitational lens, it should be able to write that in a description, not just focus on the number of spiral arms. And so what we did was we took a small data set of around, there's 64 galaxies. We made it small because, as you'll see, it's actually quite costly to evaluate. And these specific galaxies had volunteer answers from Galaxy Zoo, where the volunteers were asked questions like, does this galaxy, have spiral arms, and how many spiral arms are in the image? And so those are our ground truth labels. And then from the description, the general description, remember, we had to put, it into this format such that we could compare against the ground truth answers for the questions. And so what we did is we used another language model, and this is very common to use a language model judge during benchmarks or evaluations to take in this description and answer the exact same questions as the volunteers. And so at that point, we could directly compare the answers derived from the description to the volunteer answers. And we could see that, in this description, it said 2 spiral arms. The actual answer is 3, so I got that question wrong. And if you look at the percentage of questions that were answered correctly, for our models, from OpenAI and Google, they're around 50% of questions were answered correctly. So it's obviously, not perfect, especially when counting spiral arms, but it's good enough, as you'll see, for making a search engine that seems to work. And so if you actually look, this is, on the y-axis, is the percentage of questions answered correctly in our little benchmark, and on the x-axis is the estimated cost if we were to use that model for 100,000 images. And as you see, the models can get very expensive, and for not much gain after a certain point. But really the purpose of doing this benchmark was to pick out the best model for a certain cost. Our budget was like around $100, and as you'll see, GPT 4.1 Mini is, has decent performance for relatively low cost. And also you'll see here, we also tested open models like Qwen 3 that we could run on our own GPU clusters. And, the largest model is somewhat similar in performance to GPT 4.1 Mini. It's slightly worse, but it's actually, quite a large model. So it actually, it takes a lot of GPUs to run. So we just went with the OpenAI models. And so, okay, so we wanted to make a search and yeah, question.
Could you go back a couple slides?
Sure.
You got your AI judge there.
Yeah.
Why didn't you simply ask the LLM the questions that the volunteer galaxy suited of the original image?
Yeah, so that's a great question. So generally, we wanted to, what I'm going to show you is that we want to generate general descriptions for a large amount of images to then train our search engine. And so we wanted to explicitly test the model and the prompt to generate these general descriptions for our search engine. And so that's why we built the benchmark around this general description prompt. We could, you're very well right, that we could just give it the questions about the image and have it directly answer that. But it's not what we were wanting to test here.
It just seems that would be a better test of how good the models are.
You're totally right. It would be a better test.
And if you're going to at some point use the galaxy images as some kind of truth model, then the same procedure used to evaluate those images by the humans should be done.
Yeah,
with the AI.
I agree. It's a slightly different question what we're asking here, though.
Okay.
Yeah, we were going for general descriptions. Yeah. But that is a good study. Good question. Okay, so now we've picked out our model, and we also have a prompt that's just, generate a general description. We tried a few different prompts, which I won't go into, but we have a way to turn images into captions. So we wanted to build a search engine for all of Legacy Survey and Hyper Supremacam, which we access via the multimodal universe, which Raphael was a big part of, which is great. And the issue is that these data sets, they have over 100 million images of galaxies. And if we were to caption all of them with even the mini model, it'd be $50,000, which we did not want to send to, we didn't have the money to send it even to OpenAI. And so we had to come up with a lower cost method. And so our low cost method for going from unlabeled data, which is our images, and transforming them into a text searchable space is to first generate a training set for 300,000 random galaxies and write descriptions for them, and then train a search engine using contrastive learning, which I'm going to show you allows us to put the images into a space where we can search them via text. And so specifically how contrastive learning works, if you haven't heard of it, its entire goal, as I said, is to take an image, to embed it into a latent space, so turn it into a vector embedding that describes the phenomena in the image. And then in the same space, you want to be able to embed text, so turn text into a vector embedding that describes the semantics described by the text. And what contrastive learning does is it learns a transformation such that the images are aligned with the text in this space. And specifically what we're doing here is we're actually using the AION-1 model from Polymathic, which is essentially a model that was trained on this data set on a ton of different image data sets, as well as other data sets. As you'll see, it's a foundation model. And it's able to create, pretty good embeddings off the bat for describing the images. And we're also using this OpenAI text embedding model as well. And what we're actually training during the training process is we're training this very small MLP on top of the embeddings that literally just, takes a matching image and text pair and aligns them in this space. So the image and the text embedding are over top of each other. Yeah.
So you are using OpenAI's embeddings.
Yes.
In the process of doing the contrastive alignment, you just projected the frozen representations for the LLM into something else. You did not have the ability to fine tune the LLM, right? So you took the representations and then projected them with those frozen representations. Yes.
So the goal is to start with already text embedding that can describe the text and the content within. And so we just went with already pre-trained model that can produce these embeddings. And so we didn't fine tune it. The thing that we're explicitly training is a very small, MLP on top of it for the contrastive learning. Yeah, good question. And so, so after the contrastive learning, what we have is we have a way to go from unlabeled images, project them through the model that we trained into this latent space, And this latent space then is accessible by text. So then you can take a text query and project it into the space, and the nearest images to that text embedding should be images that match your query. And so these are real results and also a real projection of the latent space. So we can see that, it's working. I'm going to show you more examples later. And also, on an initial test of just, did this actually work, is to embed example images for like spirals, mergers, galaxies with tidal streams, and also gravitational lenses, and see if those, if the text embeddings for the text queries, land roughly in the same space as the example images. This is just a very initial test. And we see that it actually, it works in this 2D representation. Maybe the spiral galaxy text, is not over top like the grand design spiral images that we embedded. So we need a much more systematic test of these search capabilities. And so in order to do that, we set up, another benchmark where we can very easily evaluate, does the text query visible spiral arms actually retrieve galaxies in the top 10 results that have spiral arms, as judged by galaxies votes. So these are the fraction of volunteers that voted whether a galaxy actually has spiral arms. And so we're searching over this benchmark data set that actually was the same one used in the AION paper, but they were evaluating it on image similarity results. So they were trying to find the most similar images to a query image that actually does have spiral arms, and seeing, how many of the top 10 results actually have spiral arms. And so these are the results for spirals, mergers, and lenses. These are like the top few results that are most similar to this image for AION, and also most similar to the text embedding for visible spiral arms. And you'll see that when you search by images and trying to find the most similar image, you're very sensitive to your query image. So like in AION, they actually had like 1,000 example images with spiral arms. And they, as you'll see, like we're gonna come up with a metric to actually determine how good the search was, but they averaged over all the queries. But you'll see that it's retrieving images that are exact matches or very similar matches to this query as expected for image similarity. And for some of them, like there's not obvious visible spiral arms, but it matches the query image. And so I think this is an example of why text is beneficial here, because you can specify the phenomena that you want to find. You can specify, hey, I'm looking for images. They don't have to be similar, but they have to have spiral arms. And you also see that, some of the results, like searching for merging galaxies, you might see, that they might not necessarily be merging here. They might just be like coincident. And that could be a result of like GPT-4, when it wrote the descriptions, it would say, okay, if two points are close together, then they're merging. Yeah, sorry. Go ahead.
So the first row here is the similarity search when you only present the image.
Yes.
The second row is when you only present the text.
Yeah.
Is it possible to also present both?
Yes.
Okay.
And I have done this a lot. I don't have like systematic tests of this, but I have it available in the public app where you can search by image embedding plus text embedding. And I found it to be actually quite useful. So that could be a whole other study, which is cool. In that case, you could think of like, hey, I want this galaxy, but bluer, or I want this galaxy, but more disturbed, which would be really cool. And so one of the most difficult one here is like searching for gravitational lenses, but as you'll see in like the top results, we see two confirmed gravitational lenses that were already known. And so the metric here that we're using is NDCG, which is normalized distributed cumulative gain, which is from like document retrieval. But essentially the idea of this metric is like out of the top 10 retrieved images, you can look at how many are actual lenses. And then for spirals and mergers, like this relevance score, which is the fraction of volunteers who voted it as actually having spiral arms or actually being a merger, does go into this score, as well as like the position of where it shows up in the top 10. But really, 0 is bad and 1 is like perfect. And when we compare our text-based search engine against image similarity search, we see that, it's much more accurate at actually coming up with like, all the galaxies actually have spiral arms compared to image similarity, which you can't specify exactly what phenomena you're looking for. And so that's great and all, but as I said at the start, typically if you want to find a new phenomena, you're going to use actually not image similarity, although it's like kind of like a newer thing. You're going to train a supervised model that is specifically built to classify whether an image is a spiral galaxy or a merger or a lens. This is typically how people do it. So we can also compare against supervised models that were explicitly trained for classification. And so to do that, we use the Galaxy 10 benchmark, which had, it has the models classify a given image into one of 10 classes. And so what we find is that we're able to do zero-shot classification with our AION-Search model. So we can actually get classification without training it to classify, where we explicitly, and how we do this is we explicitly take an image, we embed it into the space with our AION-Search model, and then we take the 10 classes and all of their text labels, embed it into the same space. And what you would expect is that if you have a barred spiral image, it should be closest, out of all the 10 text labels, it should be closest to the barred spiral text label in this embedding space. And it, shouldn't be very close to like, edge on with bulge. And so in this way, we can do like zero-shot classification and compare that against the supervised models. And there what we find is that if we compare against models that were explicitly trained on this data set, they get around like, up to 90%. I personally looked at every image and did classification myself by eye, and I got 90%. And if we do this zero-shot classification for our model that was not explicitly trained to do this, this benchmark, we get about 53%. So it's able, I'm going to show you, it's able to like classify things into like spirals and ellipticals and such, but it might get confused for like loosely wound versus tightly wound or barred versus unbarred. But what's interesting is that if we then take those image representations with our AION-Search and we train a model on top of it in the exact same method that these models were evaluated on the Galaxy 10 dataset, we can actually recover the performance of our image embedding model that we used in the contrastive learning. And so, yeah.
So that's taking the embeddings. You project the image into the contrastive learning space and then take those representations and input them to a classifier.
Yes. So this is, so typically with like astronomy foundation models, what you might do is you'll, get the image embedding. So you don't train the whole model, but as long as you have the embedding, you can feed that into another, MLP neural network and train that explicitly to do this classification. And it works pretty well. I mean, it matches my performance, although I wouldn't claim to say that I got all of them, correct. And so like what's interesting is that we're able to recover the performance when we do that same procedure as our original image embedding model. And so this contrastive learning, we can maybe make the claim that it didn't destroy the morphology information, but rather it made it text accessible, which is interesting. And another thing that we can do is we can test, the model that actually wrote the descriptions that we trained our model on this same test, and we see that it gets around the same performance as our model, which is also not very surprising. It shows that our model is limited by the performance of the captioner model, which generated the data that we trained on, which is very expected. And how we're doing this explicitly is we're using the same prompt for generating a description, and then we're figuring out like what class best fits that description with the judge. And so, we're limited by the accuracy of these models. Like if we were to get better ones or use more expensive ones, then we'll probably get better at this. And this is a lot of numbers, but this is the confusion matrices. So on the y-axis is like the true classes, and on the x-axis is the predicted class. So you'll see for like our AION-Search, 0 shot, like 50% of unbarred loose spirals were misclassified as barred spirals. And I actually want to point that out because if you look at our captioner model, you'll see that like for really crazy cases, you'll have like smooth galaxies like this one, where the description described it as being consistent with a barred spiral, which clearly it is not a barred spiral. And you'll see that actually a lot of the misclassifications were along for both our model and our captioner were misclassifying galaxies as barred spirals, which is very curious. And so we did an interesting test, which is that we blinded GPT in that we didn't actually show it the image, but we gave it the same prompt. And what's amazing is that 100% of the time, it would produce a description of, it produced a description even though we didn't give it an image. And so like, it's like fully hallucinated descriptions if we don't give it an image. And 75% of the hallucinated descriptions mention the galaxy being a barred spiral, which is a very interesting failure mode. And so we're actually able to say that like this could be just like a prior in the model that it's just has a great affinity to describing everything as barred spirals. And so this is like one of the failure modes that could affect our search engine downstream. Yeah.
And perhaps what like the fraction of galaxies, is it just you guys have an overabundance of barred spirals in catalogs, or?
Yeah, it's a good question. So like if it's an issue with GPT 4.1 mini, then it depends on its training set, which unfortunately we don't know because it's closed, but it could be that like during its training, for some reason, it, was able to get higher accuracy on predicting the next word if it predicted, that the image showed a barred spiral. Although I should specify, like, we didn't further train it ourselves. Like, this is entirely just straight from the API. We give it an image and it writes a description. Yeah.
So for any of these targets that it says is a bar spiral, but it's just quite low spectral resolution. So
right. Yeah.
So this is with depth colors. Have you looked in higher resolution imaging to see whether there is a bar spiral? Maybe it's just assuming it is based on other morphological features that I tend to see.
Wouldn't that be amazing? We're all making fun of it, but if we had a better image, it turns out to be one. Yeah, this is that's a great test to do. It would be, surprising if it might actually be making a prediction there that if you had a better image, then it would be barred spiral. Or we could say like, maybe we need to edit the prompt and say, hey, if this is low resolution and you're not sure, don't just go ahead and predict what it would be at high resolution. Yeah, this might be a good thing. Good question.
Questions? I have one. Maybe you take this later, but how much physics does the model know? So if instead of saying, give me a spiral galaxy, you say, give me a galaxy that has a star formation rate of 10 solar masses per year.
Right.
Would you be able to regress on that as well with a model like this?
Yeah. You could test it out. We have the search engine. I think I have tried typing like high redshift, low redshift in the search engine, and it doesn't seem to work. Like I haven't done an explicit test where I've looked at the redshifts, but it would just like bring up galaxies that are, I don't know, that don't seem to match it. But I think this is something that you could definitely test. It would be, I don't know, like I like to think of these models as, like, you know, a human. Sorry, maybe not the best thing to say, but like it will have human biases because it's been trained on human data. And so like as a person, could you look at an image and guesstimate the star formation rate or the redshift? I assume it would be about as accurate as you. It might have, like through the papers it read, actually learned how to do this better than you. But yeah, that'd be something to test. Yeah. Sure.
So I'm trying to figure out how to trust these things and the biases, because the, GPT-4, et cetera, they're trained on all images. They don't know a galaxy from a car. And they also don't know artist renditions of what galaxies look like with captions for these beautiful images that someone puts out. So there's a lot of garbage going in. And I don't know if that's important in terms of what you're trying to do.
Yeah, I mean, I think it absolutely is important for like what exactly it was trained on. It is surprising like that the models, I'm going to use just a kind of a crazy example, but the models now are able to like solve like international math Olympiads with text. However, they were trained on like Facebook posts. So it is like there was a lot of garbage that came in, but like when it comes down to it, it's actually able to, I mean, they have trained this into it now, but it was able to, do very complicated things, even though in the training process, it did see bad captions. So mapping that to this example, it was trained on artist illustrations, yes, but it was also trained on, well, we suspect like papers, figure captions, Galaxy Zoo discussions. And so I imagine it's really leaning on the more expertise from that training data for these kind of examples. But it's hard to say, you can't say that for certain.
Yeah, because it's also trained on Shakespeare. It's nothing.
Yeah, exactly. So. Exactly, yeah. Question down.
I'm a little bit skeptical of the classification results because all of these images are probably in GPT's training set.
Yeah, this is it could be leakage, yeah.
Yeah. But then I think one of the coolest things here is that you probably can zero shot completely new surveys. And so I feel like a better test would be to do this on like Alice's team has just started.
Yeah. Exactly.
Where it's never seen those images, but definitely not on the training set.
This is actually something that I'm going to be working on with Euclid specifically, is using it to find try and find tidal streams. And so this is something I'll be trying. And I think it does, I am confident that it could transfer to the new surveys. Yeah.
Yeah, I think that is probably the coolest thing here, where you can probably zero shot to
yeah.
You can be pretty survey agnostic.
Yeah, totally. I totally agree. And so, yeah, so we turned this into a search engine that is available to the public online for free. So we use this to embed 20 million images from Legacy Survey. And in the search engine online for free, you can search for stuff like low surface brightness galaxies, or blue or red, or edge-on merging galaxies, etc. And what's nice actually is that it's already been used for around 1,000 unique searches for outreach purposes, which is great. Like I've been, saying this at like outreach talks, and people have really latched onto it and immediately search aliens, which they're disappointed in. But it's nice that it can be accessible in this way. And beyond outreach, or actually, sorry, before I get to that, one thing that I've been trying to do is use this exact same public interface to search for galaxies with streams, tidal streams. However, it's quite a rare phenomena. And so what I found myself doing is scrolling through, the top hundreds of results in order to find any examples of galaxies of streams. Because they're so rare and hard to find, you wouldn't expect to see it in the top, 5 images that show up. But what I thought of is, okay, there could be one trick left up our sleeve here where at search time, you can use a larger model, GPT 4.1, to actually say or score from 1 to 10 whether an image matches the query. So, oh, thank you. And so here we're, no longer asking it to write a general description. We're explicitly asking it, does this image show a galaxy with a stream? Score from 1 to 10. And we can run GPT-4 at search time over the top 1,000 images and score all of them for whether they show a stream, and then reorder based off that score. And so this re-ranking actually seems to be able to improve the search results at search time. And when we do this for spirals, merges, and lenses on our actual benchmarks, we can actually show that we can improve the search results across the board slightly. But by a fairly good amount. And when we actually look, what's interesting is when we try this on a lens benchmark, so images showing gravitational lenses, this one here got a score from GPT-4 of 9 out of 10 for likely being a lens. It was originally in the 800th place in our search results, but this brought it up after reordering based on that score to number 1. And unlike, any other supervised model, you get a description, which is nice, where it said like, oh, there's a distinctive arc-like feature to the left, which is why it gave it a 9 out of 10, which is really cool. Or multiple compact sources, arranged symmetrically. And so what we found is that for this re-ranking process, if we use larger models, so we tried like nano, mini, and the full model, and this on the y-axis is the number of lenses in the top 100 after re-ranking the top 1,000. And we tried larger models, and we also tried sampling the model more for any given image, and then averaging those results. We can actually get better results for our search if we pay more in compute. So the lesson here is that if you have a really rare phenomena that you want to find, you can at search time spend a lot in compute to try and improve the results at search time, which is a really cool ability. And so I've been using this along with the public search app that's accessible to everyone that I said people were using for outreach. I've actually been using it myself to try and find galaxies with tidal streams. And these are all ones that I've actually found using the public search app, using text search like galaxy with stream, using image plus text search, and going through a lot of images. I've collected this catalog of around 40, which is actually competitive with papers that were, or studies that explicitly trained a supervised model to try and find galaxies of streams. But this time I was able to do it just by, searching it on without training. And the reason why we're interested is because we can actually use the orbits of these streams to tell us about the shape of the dark matter halos for these galaxies. And there's a team that's, including our team in Toronto, that's very much in need of more examples of like very clean streams that you can trace the orbits of. And so in summary, like the claim that I'm kind of making here out of all these results is that these large language models are astronomy foundation models, in that they have been trained on all these papers and all the figures. They have been trained on Galaxy Zoo discussion forums. They've potentially been trained on like actual telescope data sets, although that would be, a bit of a stretch, but I wouldn't put it past them. And so they are astronomy foundation models. And so, currently we're building out these models like Zubot from Walmsley et al. that was, explicitly, it's a neural network explicitly trained on these galaxy images on entire surveys. And in order to actually interface with it, you need to develop like a fine-tuning data set of like, 1,000 examples of galaxies of streams, for example. Where with, these astronomy foundation models, like the large language models, you can actually just interface with it by just prompting, by just asking, hey, does this image show a galaxy with a tidal stream? And it'll give you a description as well, which is potentially very useful. And so like going beyond just galaxy images, this kind of general vision capabilities. I know some people now are feeding it plots of X-ray data, for example, or plots of spectra, and seeing how well it can actually understand those plots. This kind of general vision capabilities, I think, enables very broad applications that are now actually very easily accessible. Just through prompting, you can see if you have a new problem, how well these models will do. Which brings me to the question that I ask a lot of people now, which is, what would you do with 10,000 experts on demand? And my current answer is I'm having them write descriptions of galaxy images. But I know that this is potentially not the optimal use. I think that, from writing descriptions of galaxy images, it led to some new capabilities like a search engine to allow to search these images. But I'm sure in your research areas, you can probably think of some answers for how to use 10,000 experts on demand. And that might lead to some really exciting capabilities and results. Yeah.
So is there anything that prevents you from making the claim? I mean, other, of course, from the fact that you have only looked at astronomy data, but is there anything that prevents you from claiming that LLMs are science foundation models? I mean,
sure.
To what extent this will depend. I mean, we don't know what GPT was trained on, but in principle, if it performs this well with astronomy, it could do it with genomics or taxonomy or whatever, right? So I think you're pointing to a conclusion in which we don't need domain-specific foundation models, but rather these big LLMs are generalistic enough that you can perform these tasks accurately across fields.
Yeah, I am making this kind of claim that for any new task, whether it be in Earth observation, you have, observations of Earth from satellites, or stuff like, any sorts of these science tasks or microscopy images, for example, you could first try GPT, the latest large language model, and see how well it does and you don't need, it's super accessible. You just need prompting. You just need to ask it. And then there you could have a starting point where it either works or it doesn't work. And if it doesn't work, then you could reach for the actual bespoke scientific foundation models. So I do think that there is a purpose. Like, for example, like you were saying for regression for star formation rate or redshift, this sort of stuff. I think that I would much rather have a model trained to do that than just prompting GPT. But yeah. All right. So this was the conclusion. So the app, the code, the data, and the paper are all accessible online. So I would recommend trying out the Search app because it's kind of fun. And hopefully leads to some cool results. And I'd be very curious on all of your guys' ideas for how to test out these models to see what they can do in astronomy. Thanks very much. Sorry?
What data is it? Is it just galaxy data?
So the data that I've released on Hugging Face is the 20 million images from Legacy Survey, as well as their embeddings from my model. And then I've also released my training set, which is 300,000 images from Legacy Survey and HSC, and their descriptions as well. Yeah.
But there's no reason not to try this with Lakers, Dan, just in case. Jonathan?
Oh, yeah. I'm sorry, I came a little bit late.
That's okay.
I thought this wasn't discussed already. But there was some discussion about whether you can trust these classifications or not, and mention of trying to get higher resolution data to see
Right.
if what it detected is really there. This is kind of obvious, but I was wondering, talk of giving it new data that it was not trained on.
Right.
From new catalogs, I think LSST was mentioned. Would it make sense then to smear images to lower resolution?
Yeah.
To submit it the first time, so that the classification is very ambiguous, but the tester knows.
Yeah,
certainly what the classification is.
Yeah, absolutely. I think this would be a great test to make, to see, how its classification accuracy goes down, the lower resolution you get. And it would be amazing, like, to see if there were cases where it was actually good, where it would be, harder, or maybe a human just might, not be confident enough to make a classification, which is another thing you actually want to test with these models. Is like, it seems like GPT-4, as I said, even without giving it an image, will still output a description, so it can actually hallucinate. And so, like, there's also a degree of confidence where, like, a human might, if it's blurry, a human might just say, hey, I don't know. But the model, at this point, for the models that we tested, will still try and make a prediction.
If you're giving a new data, you should smear it the very first time you submit the data.
Right.
I think the models sometimes are self-learning.
Yeah, that's a good point. Yeah, you can test that. Good idea. Thanks. Yeah.
Rocco and then.
Yeah, so you showed in one slide in the classification, like in the confusion matrix, that you have this bias toward dark galaxies.
Yeah.
And then you're kind of doing the re-ranking and other things. How do you think the bias kind of affects, is there any effect on the bias, and is there any way to correct for it?
Yes. So we could actually test, like, the search engine and search barred spiral and see what happens if you want. Whoops, I stopped.
Or search one of the ones that got confused with barred spiral.
Yeah. Who doesn't like a live demo? I mean, theoretically, if we search barred spiral, it should come up with galaxies that aren't obviously barred spirals, which, I mean, this one is appears to have a bar. But yeah, there are some here which, it's a bit more ambiguous whether that's the case, which is one of the failure modes.
So what happens if you ask it, show me galaxies that have an AGN?
Yeah, let's see. Yeah, a lot of these galaxies, these ones haven't updated yet.
That seems to go to, like, clustered systems.
Yeah, it seems to go to clustered systems, potentially some with, like, some of these might be stars. But I've done a very interesting test where I took my whole training set and its descriptions. And then I did I think I told you about this. I did a tournament where I gave it image A and image B, and I said which galaxy image is more interesting. And I did that for the entire training set. And the galaxies that bubbled up to the top that won the tournament for the most interesting galaxies, there were some confirmed AGNs at the top, and they actually did look like AGNs, which is really cool.
I'm sorry, you had a question.
Yeah, I'm wondering about the language, the terms that are used in the searches. So when you say the word stream,
yeah,
you mean by stream. Would it be useful to, before you do your initial generation of descriptions, provide a glossary to the LLM and say, here are the terms you must use, and this is what I mean by those terms?
Yeah.
Maybe that would make things a little more precise.
Yeah, I do think that would be useful. Like, because then for the search, you can literally just filter all the galaxies for those that GPT labeled as streams, rather than have it in the general description format. The place where, it potentially you would have to have a very comprehensive glossary for that, which yeah, could be an issue. But I do think that would be worth trying. Yeah.
It seems like the AI wants to answer something.
Oh yeah, I know. Jumping in. Yeah.
Dan.
Do you include metadata in your images, like the redshift or?
Yeah, this is something that no, we don't. Not for description generation. I think it's absolutely worth it to include as much info as you have about a galaxy image to provide it for context. If it's useful for a human when describing the galaxy, then it's probably useful for GPT. So if you were to build AION-Search 2, this is something that I would definitely try. Yeah.
And have you played, so can you talk more about the way you do the contrastive learning? Have you played with different ways of connecting it, like generative or other ways of connecting a text and image embeddings?
Yeah, so honestly, I didn't do much of like searching over different architectures or different even like methods for contrastive learning. It was the fairly simple. I just did like info, nice and very small MLP layers over top of like the AION and the text embeddings. And so I think this is very ripe for exploration, for improving these results. I'm sure you already have ideas for how to do this, how to improve upon this. Yeah. Good question. Yeah.
Okay. So I'm wondering how well the search does with image artifacts. I see one
Yeah.
right there, right in the middle. Have you looked at that? It gives any results.
That's some good stuff. So
That's a pretty good one.
yeah. And this was good. I actually used this in the process because there was another team member at Polymathic who was specifically working on like getting imaging artifacts out of the images, and they wanted to know like the breadth of imaging artifacts in a survey. And then so I literally pulled up my phone, went to the website, searched up imaging artifact, and then showed them some that like they didn't know of, like whatever's going on here, which was really cool. Yeah. Good question.
Yeah. It's a fantastic result.
Oh, thanks. Thank you.
Any other praise? I mean, one thing that I like about this is the fact that you sort of inverts the anomaly search problem to like, because so far astronomers have been very good at designing anomaly detection algorithms and coming up with a long list and then trying to scratch their heads to figure out why is this anomalous? Whereas here, you sort of type exactly the sort of anomaly that you're looking for. Of course,
right.
It would be hard to ask for the unknown unknowns.
Yes, absolutely.
Describe it. But so I wonder when you would come out, you say, what is the most anomalous object that you find in the data set and why? And something like that.
I'm thinking of exploring this and setting up these tournaments that I'm describing, where you could imagine giving it Euclid, and then I might be able to come up with a way to like come up with the most scientifically interesting images in the survey. And the reason why I'm confident about that is I think that these models, these language models, are probably our best chance at understanding what's, automating the concept to determining if something is scientifically interesting, because they've read the literature. And so previously with anomaly detection methods, you might come up with image artifacts as anomalous, but it's not interesting. And the concept of interesting only comes from if you understand the literature. And so I think this could be very interesting to explore.
And yeah, there's another question, comment. That.
I was just curious about what would happen if you looked at completely out of distribution events. Like if you asked this to search for a dog or something.
Yeah, I think I had a good one. Snowball.
Image of Boston.
So it comes up with some galaxies that I would describe as like snowballs. And so what I expect is happening here, this is obviously I've done a lot of playing around and also looking at the public outreach one, searching for aliens and stuff. But this one, I'm pretty sure it comes from the fact that our OpenAI text embedding already puts snowball near like white, spherical, that kind of stuff. And so it actually works with our search engine, which is cool. Yeah.
Do you think there's any use in like bounding your latent space to be within the realm of astronomy?
Yeah, so
Leaving it that freedom is.
I mean, with that, then we would, I think there might be use for it, like for moving to a specific text embedder that was explicitly trained for astronomy, for example. Yeah, I'm not sure how much improvements it would lead to for search results. It's hard to say. Yeah.
So with decals, there's a lots of like repeated observations. So is your model able to pick up like time domain phenomena?
Oh, that's a great question. Yeah, I think this would probably be another study where you could, in principle, provide descriptions of multiple images over time and see if it could understand what's going on. I think that's absolutely worth studying. You could try that for like supernova difference images too. And so, yeah, I think that's worth it. Good question. Okay.
Well, it's 12 o'clock, so people are already thinking about those sandwiches behind them. So maybe let's let them eat. And Nolan's still here today and tomorrow. So if you guys are interested in chatting with him, he is sitting in 2O. What do you remember? Well,
Mike's
the post office is in this.
Yeah.
Where Mike is. So reach out if you want to chat. And thank you so much for an
Thank you. Thanks. Thanks.